In an ordinary computer, you could put in a zero to an algorithm and run the algorithm and get an answer. And then you would put in a one into an algorithm and get the answer. But you have to run it twice, right? With a quantum computer, you could um, put in a state that's both zero and one at the same time, run it once through the quantum computer, and
Mm.
then get some answer out of it. And because of that, you get this kind of parallelism out of the quantum
Mhm.
computer.
Yeah.
That it does it. Now, how to measure it and what the algorithm is, that's very complicated. Okay.
But wait a minute, John. Let's get into this parallel computing a bit, because I'd like to understand this a little bit better. This is how I think about it, and I think, just correct me if I'm wrong. I draw a parallel to the English language. So in the English alphabet, we have letters that combine into words. So if you want to write the word house, you need to use a combination of
Right.
letters. On the other hand, in Chinese language, you can use one sign for house. So if you wanted to change the word house in the English language to some other word, let's say table, then you would have to do operations on each and every letter one at a time, basically. But on the other hand, if you would take the word house and then translate it into Chinese first, which is one sign,
Right.
then you could do one operation on that sign and change it into table, the Chinese word for table, and that would only take one operation. You wouldn't have to change a bunch of letters. You would just change that one sign, and then you would have to translate it back to English again to get the answer. Uh, is that a good parallel to what's going on?
Yeah, it's an interesting parallel. I hadn't thought of this.
Hmm.
It kind of is an idea of using coding, which in data compression. That's a better
Yeah.
word, where
Right. Yeah.
you compress it to this Chinese symbol. And I,
Right.
I
Yeah.
would say that quantum mechanics is different than data
Hmm.
compression. Okay,
Okay. Yeah. Yeah.
it's an
Yeah.
interesting analogy, but I'm not quite sure
That
that's
it works.
let me explain. Maybe you'll understand why this parallelism is so important. So with one quantum bit, you get a parallelism of two. Okay, and which is nice, but okay, I can just run my classical computer twice, and it's fine.
Mm.
But
Yeah.
what's interesting and profoundly important about quantum mechanics is the way that it scales as you have more and more complex encoding, like the word house, right? So, and I'm thinking of an analogy you might like here. So, if you
Mhm.
have two quantum bits,
Yeah.
and then they're each in a superposition as zero and one, that means you're actually running four states at the same time: zero, 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 one, one, zero, and one, one. Okay.
Okay.
And if you have three qubits, it's zero, 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 one, zero, one, zero, zero, one, one. Then there's eight states. Okay.
Hmm.
So
Right.
every time you add a qubit, you're doubling the number of parallelism,
Right.
which means it's growing, what we say, exponentially. It's growing very, very large.
Somehow this still seems like compression to me. Somehow this still seems like you can encode more information in a smaller piece of a smaller bit than if you would use a classical computer, because you have more combinations, right? That's the main sort of geist of it, right?
And this is what happens in classical computers: is you make bits into bytes into longer words. You can
Mm.
encode more and more complex information, which we all know about in our computer. I mean, it's complex
Right.
information. But the
Yeah.
problem is, in a classical computer, as you make the bit strings longer and longer, you still have to process that information one unit at a time,
Mhm.
one byte at a time, one word at a time, something like that.
Right.
Whereas in a quantum computer, you could process all the information. So you take house and table and chair and
Hmm.
a ton of words,
Yeah.
and all of those words can get processed in parallel. right?
Right. Yeah.
And you can convert them into Chinese and then back again, all in parallel. You don't have to
Hmm.
do it, 1,000 times. You just do it once.
Okay.
Your
Okay.
analogy is talking about the how powerful it is to string bits together to make things more and more complicated. What the
Hmm.
quantum computer says is as you make it bigger and bigger, it's still you can make it into one operation. You don't have to do it.
Hmm.
You can process house and table and chair in one operation.
Right. This is where it gets very strange, though.
So that's what's wonderful about it.
Yeah,
Exactly.
exactly. And I guess that's why you constantly want to try to find parallels in the normal universe to sort of try to wrap your head around it. But then it sort of escapes your normal parallels anyway. If you have a question for John, just write it in the comments field before the end of July 2020. If you liked this video, why not make it official? Press the subscribe button and then the bell beside it. And while you're doing that, why not also open your window and shout out the name of my channel? Stir-Fried Fascination! Thanks for watching, and see you in the next one.